Okay, we do have two sections of today's meeting. One is continuation of our Thursday section because of schedule conflict. Rebecca will complete our set of knowledge about Gaussian, and what she's presenting is critically important if you plan to model chemical reactions.
Okay, so welcome to our presentation. The first part is about preparing Gaussian input files without phase view. And we start off when we have the geometry for our molecule. We typically store it in a .xyz file. And we go from that. And if we don't want to modify this file, we have to copy it into like a com file because this is the input for Gaussian. So we can either use the cp command to copy it, or the mv command, so then we don't copy the file, we just rename it and basically change this file. I would copy it so we always have the geometry, but that's up to you. And once we have the .com file, we modify it with the vi command. So and then we press I for insert, and then we change it. And the first line, oopsies, we specify the processors we want to use for the job. And in general, it's like the larger your system is, the more processors you want to use, so the job finished in a decent amount of time. And it's very important that you start with the percentage sign. Yeah. And after that, you specify the memory. And it's pretty similar to the processors. The larger the system, the more memory you have to provide. And then you specify the name of the check file. Last time I mentioned the check file as like the checkpoint. And it's very important to give it like a meaningful name, because in some cases you want to find it after the calculation finished. I mean, usually we look at the com and then the log file, but sometimes when your calculation doesn't finish in the time, you really want to use this check file, so it's important to give it a meaningful name so you can find it afterwards. And then, really important, we have an empty line. And then we have the command line where we specify which the job type and which basis set we use. We can also specify pseudo potentials if we have heavy metal elements or solvents. And it's important that you start with this hashtag. And then we have another empty line, which is really important. And we have the job title. And then we have another empty line, which is really important. And before we have like the coordinates, we specify the charge and multiplicity. We talked about that in the last lab. Like the charge is clear, like the charge, and the multiplicity is 2 times the spin plus 1. So we just specify whether that's like singlet, doublet, triplet. And then we have the coordinates, which we got from the XYZ file. And below the coordinates, you can put additional input, for example, the connectivity, or if you have a mixed basis set. So, for example, if you use a different basis set for different atom types, you will have to specify it below the geometry. And I cannot highlight this enough. You have to have empty lines at the bottom of your input file, like at the very bottom. There have to be empty lines. And when you modified the file, you save it by using like WQ, like write Q, when you exit the file. Otherwise, you won't save it. And then you can submit it with our known command. Any questions about that?
I have a question.
Yeah.
You mentioned you need a percent sign and the hashtag. What is it?
What?
Okay, so for your first few lines of code,
it just basically tells the program like what kind you are specifying at the moment. So the first 3 lines, they are called link 0 commands, and they just always start with a percentage sign. And then the command line where you specify your job and basis set and everything, it just always has to start with the hashtag. So the program knows, okay, it's a hashtag, now it's the important stuff. So kind of like that.
In some languages, the text after hashtag doesn't make sense, but usually it's just a comment or just a illustration, something like that. We have same thing maybe for this software, or like
Here it does make sense.
so it's a comment.
It's not a command.
But
it's not a command. It is a command.
Oh, it's a comment. Okay. Because in for instance, Unix or some other languages, you use a comment, or for instance, in MATLAB, use a percentage.
But
we leave a comment.
It is
so
not
it's a comment.
Comment. Yeah, I'm sorry. But does it make sense now?
No, it does.
I think in Linux you cannot put comment.
Yeah, like you write like the code, but here you put the command.
Yeah, I get it.
Okay.
Thanks.
Okay, so I move on to the second part. It's about the scan of reaction coordinates, and we have ethanol, and assuming, and we have Gauss view again. It appeared, and we can use it, and we will. And we want to know how the energy changes if we dehydrogenate. Yeah, the OH group. So we're looking at this reaction, and to do so, we have Gauss view, and first we have to specify the redundant coordinates. So we go to Edit, and then select redundant coordinates, and obviously we add one to the system, and here, so we want to look at this bond when this bond gets longer and like the hydrogen moves away from the oxygen and we like break the bond. So we want to look at the bond. These are the number of the atoms. Do you remember when you go to Gauss view and then to the builder and then select atoms, that the atoms have numbers? So it's the both numbers of the both atoms you want to look at, like from the bond. And yeah, the job is we scan the coordinate and we take 10 steps. It was maybe a little much, maybe 5 steps. Oh yeah, and every step is 0.1 angstrom, so it looks at the energy every 0.1 angstroms that the bond gets longer. And then we click OK. And we, and then when we go back, we go to calculation setup and set up the job that we want to submit. And the job type would be scan. And the redundant coordinates is what we use when we submit it. So, yeah. And this is our output, and like the graph on the top, you have the total energy and the coordinate that we just specified. So we start here, and then we have 0.1, 0.1, like the points, the energies, and we can see that the energy rises as we move the hydrogen further away from the oxygen. And this graph is the root mean squared gradient, which basically just shows us how this potential energy surfaces behave. So it's like a differentiation. Does it make sense?
So if you remove your hydrogen to very far distance, this air mass gradient norm will become 0, right?
Yeah. Yeah, and that's the output we get. And does anyone have questions about that?
Is it the last
also you can see like it shows a little video of how it like moves the hydrogen away. I don't know why it like switches the oxygen, like why it flips the molecule, but basically it just like moves it away. That's what it did during the calculation. Yeah.
Very good. Yeah, but thank you very much. Any questions to this presentation?
Oh, what's the meaning of the RS and if you could
RMS is a root mean squared gradient.
So the bottom line is that maybe derivative of the differentiation of the
Yeah,
outline of that.
That's what I
Actually, it's the slope of the top line at each point, maybe.
More questions?
And that's why it's becoming zero, because once the hydrogen is so far away, it doesn't change. Like it doesn't matter if you move it further away or not, and that's why it's.
Last chance?
I have a question.
Please.
So if the bottom is like the derivative of the first, and you're measuring the energy at a certain first, wouldn't the derivative also converge to time? Because it's the rate of changing of this.
Oh, so at the moment, like when you move the hydrogen further away from the oxygen, the energy rises, but at some point, but it rises like fast, and then it like rises slower, and at some point when the hydrogen is so far away from the oxygen that there's like no connection at all, the energy won't change because it's just too far away, and that's when the energy doesn't change, the derivative is zero.
Yeah.
Does it make sense? Was that your question?
It does. I guess maybe if you change the scan step, you actually have the upper graph to show what the rate of change, like different slopes as you're changing along. That's what I'm curious.
The lower panel is not the target. It's just a byproduct to check if error is big or small. But the main goal of this calculation is to get the top line, which can be used to reparameterize force field. Or it can be used to explore specific reaction. So it is potentially something that we were studying at lecture 7.
So this is norm. This is norm.
Huh?
This is norm. That means it has been normalized with respect to highest point. That's why it's getting up and down.
Very good discussion. More questions? Question 1, questions 2, questions 3. Thank you very much.